Hello everyone. In this video I am going to show you how to calculate phase change type of problems. These are the only types of calculation problems that we're going to do in chapter 10. The rest of them are going to be mainly conceptual type of problems based on intermolecular forces. But towards the end, so when we're looking at the phase changes, we have these types of curves, and we will learn to calculate the amount of energy that is needed, so is absorbed or released when we're either heating or cooling according to a phase change curve. We're mostly going to deal with water, but understand that any substance has similar phase change curves. They just differ a little bit in where the melting points and boiling points are. Okay, let's start. The first problem: calculate the total amount of heat absorbed in kilojoules when 35 grams of water is at minus 35 degrees Celsius is converted to steam at 125 degrees Celsius. I have the phase change curve here on the board. There's my temperature axis here. So I start at about minus 35 degrees and I want to end up at 125 degrees Celsius. So I'm going to walk you step by step where we're going to find ourselves in this curve. First of all, let's look at the temperature. Even though it says water, and when we hear water, we immediately think, oh, it's liquid. But because it says 35 degrees or 35 grams of water at minus 35 degrees Celsius, I know that because I'm at minus 35 degrees Celsius, it is ice, not water liquid. So I'm starting with ice at minus 35 degrees, and I want to end up at 125 degrees, which would mean steam at 125 degrees. If you look at these areas over here of the curve, I have broken them down by, well, here in this horizontal line corresponds to the melting point of water, and this other horizontal line corresponds to the 100 degrees Celsius, which is the boiling point of water. So these are the divisions, if you will, between phases. I have below this line over here, the first line, I have ice. Once I hit this line, I'm melting. So here above the line, I have water. In between the melting and the boiling, I have liquid water. Okay, and once I boil, so above the line that stands for the boiling part of the evaporation of water, I will have steam. So I have ice here, water in this region, and steam all the way up here. Notice the sloped parts of this graph. Those sloped lines correspond to areas of the graph where the temperature is changing, right? Because I have a slope, the temperature changes along this slope. It changes until it reaches one of these plateaus, and then the temperature doesn't change anymore. For these, if I am anywhere in those lines, slope lines, so for those parts, I am going to be using Q equals mc delta T, because I have a delta T, I have a change in temperature, which means I am along these lines. Once I hit these horizontal lines, my delta T is 0. That's what this line doesn't change, which means it's constant at 0 degrees, which means I don't have a temperature change. It's 0. Because it's 0, that would make my Q 0, but that we know that that's not the case. So we have to use different formulas for these plateau parts. And we'll get to that in a second here. I want to point out the difference, though, between the Q equals mc delta T in the three different regions. They look like the same formula, but we have different delta T's, and we're going to have different C values. The C is the specific heat. In the problem, in your PowerPoint slides, you'll see that at the bottom of the problem, you have a bunch of values. Those are their constants that are given to you. And if you see, you have 3 values for C. which is the specific heat. That we're familiar with the water, the liquid part, MC delta T. We covered that in chapter 9 in almost every problem that we did. And the C that we used there was 4.184 joules per gram degrees Celsius. That's for the specific heat of water liquid. However, I don't have liquid for all of these parts of the graph. I have ice over here and steam over here, and those have different specific heats. So I have to use the particular specific heats for ice when I'm dealing with this part of the curve, and then when I'm up here dealing with this part of the curve, I have to use the specific heat for steam, and obviously here for water liquid. That's the difference between these Q. Otherwise, they'll use the same amount of mass in grams, and then the delta T will be dependent on where I start and where I end up. Now let's talk about the plateau parts. These do not have, as I said, they don't have a delta T, so we use different formulas. For the melting part, I use Q equals N times delta HF, which stands for the heat of fusion for water. And there's a value that is given to us that's associated with that. Up here is N times delta HV, which is the heat of vaporization of water, because I'm vaporizing, I'm turning water into steam up here. Here I'm melting or fusing, depending on which direction I'm going. Here I am evaporating or condensing, once again, depending on which direction I'm going. N, little n, then stands for the number of moles of water. I am going to be using both mass in grams for Q equals MC delta T's, and I'm going to be using the number of moles for these plateau parts. So I need both. Therefore, that's what the first thing I'm going to do is convert that 35 grams of water that I'm given into how many moles of water I have. Let's start. 35 grams of water. Convert that by using its molar mass. I know that 1 mole of water weighs about 18 grams. I didn't do that. You can do a 16 for oxygen and 2 hydrogens, 18, about. So I delete the grams and I'm left with moles. So this is going to be about 1.94 moles of water. Now that I have all the values that I need, and if you're going to use these values for the plateaus, these formulas for these plateaus, then you're going to have to convert your mass in grams into moles. You're going to be using both depending on which part of the curve you fall on. Let's start with step 1, Q1. My step 1, I am at ice at minus 35 degrees. And I'm going to add energy to this piece of ice. So I'm right here and I'm following this sloped curve until I hit the 0 degree point. At that point, the temperature is not going to change anything because then I'm starting to melt. But for that part of the curve, the sloped curve, I went from minus 35 to 0. And I need to calculate how much energy I have to add to the system. This is M times C for ice times my delta T, the temperature change. The mass is 35 grams. I'm not using moles for this because moles are only used for the plateau part. The slope parts are using mass in grams. 35 grams times the C for ice. It's not going to be 4.184 because I have ice here, not liquid water. It's 2.03 joules per gram degrees Celsius. Notice how even the specific heat dictates that the mass be in grams, not moles, because I have joules per gram degrees Celsius, meaning this mass has to be in grams to cancel out. Times, let's talk about the temperature change. I started at minus 35 and I end up at 0 degrees. which means this is my final temperature for this little step. Minus or 0 is my final temperature, and minus 35 is my initial temperature. Don't forget that minus. I have 0 degrees minus a minus 35 degrees Celsius. My degrees cancel out, my grams cancel out. This will give you 35, and if you do all of that math, that will give you 2,486.8 joules. Now, the question asks me to calculate the energy in kilojoules. Therefore, I have to convert the amount from joules to kilojoules. Here's how I do that. 1 kilojoule has 1,000 joules. My joules will cancel. So basically, I take my amount in joules to convert it to kilojoules and divide it by 1,000. That gives me about 2.5 kilojoules. That is my first step. In that first step, I added 2.5 kilojoules to convert to take ice from minus 35 degrees all the way to 0. Now, I'm right here at this point. I have 35 grams of ice at 0 degrees Celsius. Now, if I keep adding energy, because I'm at melting point for water, it's not going to be sloped anymore. It's not going to change the temperature, but it's going to stay constant until I melt all of that ice. So somewhere here in the middle, I will have a mixture of ice and liquid. And then once I get to the other end of that line, the horizontal line, at this point right here, I will have all water at 0 degrees. Notice that the temperature hasn't changed. I changed phase here. I went from ice to water at 0 degrees. I can't use delta T because temperature doesn't change, so I have to use this particular formula. So Q2 is equal to N for the number of moles times delta HF for delta H of fusion, the heat of fusion, for the enthalpy of fusion for water. And I calculated up here 1.94 mole of water times, this is 6.01 kilojoules per mole. Now, once again, delta H of fusion tells me that this N has to be an amount in moles because I want kilojoules. The only way that my moles will cancel out is if I have an amount in moles up here for N. My moles will cancel, and this gives me 11.67 kilojoules. That's my step number 2. Okay, now I'm right here. So I went up here from step 1, from here to here. That's my step 1. Then step 2 is I melted all of the ice. So right now, after step 2, after I added 11.67 kilojoules of energy to that 2.5 initial, I am at this point. I have melted all of the ice, and I have water, liquid, at 0 degrees. I'm still at 0 degrees. But I'm not stopping there because I have to take it all the way to 125. I can't do it directly. I can't take water from 0 to 125 because I have to go through another phase change. So I can't do delta T of 125 minus 0 degrees. This isn't going to work because at 100 degrees, I go through a different phase change. So I can't do that. I have to break it through 2 more steps. So what I can do, though, if I increase the energy that I'm dumping into the system, I take this water from 0 degrees from this point, and I increase its temperature, increase it till I hit this point, which is the boiling point of water, 100 degrees Celsius. I can do that. I can take water liquid from 0 all the way to liquid at 100 degrees. And I can calculate the amount of energy that's needed to do that by going back to Q equals mc delta T, but with a C for liquid instead of ice now. Let's do that. Q3 is equal to mass times the C for water times delta T. Mass doesn't change, it's 35 grams, multiplied by 4.184, we should know this number by now, joules per gram degrees Celsius. And now my delta T. Where am I ending up? My final temperature is 100 degrees. That's where I'm ending up. And my initial temperature is 0 degrees because that's where I started from. So 100 minus 0 degrees Celsius. This cancels out. My grams cancel out. If you do all of that, it will give you 14,644 joules. To convert that to kilojoules, you just divide by 1,000 to give you 14.6. I'm going to cut it off. Kilojoules. That's my step 3. So now I have taken, with these 3 steps, I've taken ice from minus 35 degrees all the way to liquid water at 100 degrees Celsius. But I'm not stopping there because I have to take it all the way to 125. But once I hit that 100 degrees, I hit the boiling point of water. I have to go through this plateau part. I have to evaporate that water. And as I move across this line over here, I am evaporating the water, which means I'll have a mixture of the two. I'll have some liquid water and some gas, steam, basically. And as I end up here at the end, so at the right-hand side of that line, I'm going to have steam at 100 degrees. Once I have steam at 100 degrees, then I can increase the temperature one more time. But let's calculate the amount of energy that is needed to evaporate all that liquid water and take it from water at 100 degrees to steam at 100 degrees. My temperature doesn't change, so I have to use this formula. Q4 is equal to N times delta HV for vaporization. My N is 1.94, that hasn't changed, mole times delta HV for water is 40.7 kilojoules per mole. My moles will cancel, and if you do that math, you should get 79.05 kilojoules. Now that I have added this much energy, I have taken my ice from minus 35 all the way to steam at 100 degrees with adding all of this much energy so far. But it tells me that I have to have steam at 125 degrees. So I have one more Q equals mc delta T to do. So I'm taking here, I have steam at 100 degrees, and I have to heat it up till I get to 125. That will require one more step, which is mc delta T, but with the steam for specific heat of steam instead of water. So let's do the last part of the puzzle. Q5 equals M times C for steam, I'm going to write ST, times delta T. My mass is, once again, 35 grams, times C for steam is 1.87 joules per gram degrees Celsius, times, now let's look at the temperature change. I end up at 125 degrees, so that is my initial temperature, 125, and I started at 100 degrees. That is my initial temperature. And this is my difference then. So degrees Celsius will cancel, grams will cancel. If you do this math, this will give you 25. If you do that math, you will get 1,600 36 joules. And if you, to convert it to kilojoules, you divide it by 1,000, and that will give you 1.6 kilojoules. That is the last step. Now that I have all of the pieces together, the very, very final thing I need to do is add all the steps together to get the total Q, the total amount of heat required. So I'm going to erase this part here because I ran out of room down below here, but that's all. And I'm not going to write all of the values because you have them all written down, but to find Q total then, which is the last step, it's going to be Q1 plus Q2 plus Q3 plus Q4 plus Q5. And if you add all of these together, and notice they have to be in the same unit. For this particular problem, we were told that we had to report the answer in kilojoules, but you don't necessarily have to do that. You can report it in joules. It doesn't matter, but the Q equals MC delta T parts, so the sloped parts are going to be in joules, and the horizontal lines, these two steps, they're going to be in kilojoules. So convert either kilojoules to joules or joules to kilojoules so that they're all in the same unit. Then if you add all of these values together, you should get, with significant digits, 110 kilojoules of energy. It takes 110 kilojoules of energy to heat up 35 grams of ice from minus 35 degrees Celsius all the way, converted all the way to steam at 125 degrees Celsius. That is how much energy you need. You don't have to work through all of these every time. It will depend on the problem. For this problem, we had 5 different steps. This is the longest problem of this type that you will have to do. But you can see that you may not need, depending on where you start and where you end, you may not need all 5 steps. So if I had said, we start at minus 35 degrees and I end up at 90 degrees Celsius, well, then I don't have to worry about that part. All I have to do is heat up. So I'll still have this. I'll heat up the ice to 0 degrees. I'll melt the ice. Well, I'll have water at 0 degrees. Then I'll heat up the water from 0 to 90. And that will be the end of my steps. I don't have to convert it to steam because I stop at 90 degrees. Or vice versa. You can start at water at 0 degrees and convert it all the way to steam at 100 or 150. So it just will depend on where you start and where the question has you end. Whether you will have all of these steps or just a few, how many of the 5 steps you will have. But this is the longest one, and then I'm going to do the last slide, those 3 problems, and those they're not as long. They don't have all the 5 steps. So I'll show you examples on what to do there. Okay.